Welcome to this specialized mathematics lecture on arithmetic progressions, designed for Class 10 students. In nature and daily life, we observe many beautiful patterns: the spiral of sunflower seeds, the cycles of calendar days, and even our periodic savings. An arithmetic progression, commonly abbreviated as AP, is a sequence of numbers in which each term is obtained by adding a fixed number to the preceding term. This fixed number is the constant difference, called the common difference. The progression represents a model of steady, linear growth. Observing the stepped staircase on your screen, trace how each step climbs by a constant, uniform height. Master this arithmetic sequence, and you unlock the key to analyzing financial accumulations, acoustics, computer memory indices, and the steady progressive patterns structuring our universe. Let us formalize the algebraic structure of an arithmetic progression. The standard form of any AP is written as A, then a plus D, then a plus 2D, then a plus 3D, and so on. Here, the variable A represents the first term of the progression, which acts as the starting coordinate or base. The variable D represents the common difference, which can be positive, negative, or zero. If D is positive, the sequence grows upwards. If D is negative, the sequence decreases steadily. If D is zero, the sequence remains constant. Tracing the 3D staircase visualization on your screen, notice how step 1 starts at height A, step 2 rises to a plus D, and step 3 reaches a plus 2D. This elegant structure allows us to write any term in the sequence algebraically using only two variables. How do we find a specific term in an AP, like the 100th term, without writing out the entire sequence? We derive an elegant algebraic formula. Let us analyze our terms. Term 1 is A, which is a plus 0D. Term 2 is a plus 1D. Term 3 is a plus 2D. Term 4 is a plus 3D. Notice the pattern. The multiplier of D is always exactly 1 less than the term number. Therefore, for the nth term, which we write as A sub n, the multiplier of D must be n minus 1. This yields the fundamental AP formula. A sub n equals a plus the quantity n minus 1 times D. Tracing the step dashboard, see how this formula computes any term instantly. It gives engineers and scientists a fast predictive tool to calculate future values, sensor cycles, and memory addressing. The nth term formula drives many practical layouts, such as seating arrangements in theaters or stadiums. Imagine an auditorium where the first row has 20 seats. Because the theater expands outwards, each subsequent row has 2 more seats than the row in front of it. This seating layout forms an AP where the first term A is 20 and the common difference D is 2. Row 2 has 22 seats, and row 3 has 24. If we want to design row 30, we do not need to construct the theater row by row. We use our formula. The seats in row 30, A sub 30, equals 20 plus the quantity 30 minus 1, multiplied by 2, which is 20 plus 29 times 2, simplifying to 20 plus 58, or 78 seats. This simple formula allows civil engineers to optimize materials, sightlines, and crowd evacuation limits. What if we want to find the total sum of all terms in an AP up to a certain point? For instance, the total number of seats in the entire theater, or the total money saved over 30 months. We derive the formula for the sum of the first n terms, written as S sub n. To visualize this, imagine we represent our AP terms as stacks of blocks. Tracing the area grid on your screen, see our staircase representing the AP. Now, imagine we take a second, identical staircase, flip it upside down, and place it directly on top of our first staircase. Together, they fit perfectly to form a solid rectangle. The width of this rectangle is n columns, and the height of every column is exactly 2 a plus n minus 1 times D. The total area is n times the quantity 2 a plus n minus 1 times D. Since this represents 2 identical staircases, the sum of our single AP must be half this area. This visual staircase proof yields the primary algebraic formula for the sum. S sub n equals n over 2, multiplied by the quantity 2a plus the quantity n-1 times d. We can also write this formula in a simpler, elegant way. By splitting 2a into a plus a, the term inside the bracket becomes a plus the quantity a plus n-1 times d. Since the second term is simply our last term, L, the sum simplifies to S sub n equals n over 2, multiplied by the quantity first term plus last term, or a plus L. Tracing the derivation dashboard, see how these two formulas link together. The first formula is perfect when we know the common difference, while the second is incredibly fast when we are given the first and last terms directly. Let us see this sum formula in action for a personal saving plan, which is a perfect AP. Imagine you start a savings account in month 1 with $100, which is our first term A. Every month, you deposit a constant $50, which is the common difference D. Month 2 has $150, and month 3 has $200. To calculate how much you save in month 6, we use the NTH term. T sub 6 is $350. To find the total accumulated money saved after 6 months, we use the sum formula. S sub 6 is 6 divided by 2, times first term 100 plus last term 350. This is 3 times 450, which is exactly $1,350. Tracing the saving compounder chart, see how the linear deposits build a quadratic sum. The sum of an arithmetic progression has a famous historical story featuring one of the greatest mathematicians of all time, Carl Friedrich Gauss. When Gauss was just 10 years old, his teacher gave the class a long, tedious chore to keep them quiet. Add all integers from 1 to 100. While other students started adding 1 plus 2 plus 3 row by row, young Gauss solved it in seconds. He noticed that if he wrote the sequence forwards and wrote it backwards underneath, the columns always added to 101. For instance, 1 plus 100 is 101, 2 plus 99 is 101, all the way to 100 plus 1. There were exactly 100 columns. The total sum was 100 times 101, divided by 2 because he added the sequence twice, yielding exactly 5,050. Gauss reverse-engineered the AP sum formula. Arithmetic progressions are the core equations structuring physical acceleration. When an object falls, gravity accelerates it, meaning it travels a greater distance during each subsequent second. If a falling stone travels 5 meters in the first second, 15 meters in the second, and 25 meters in the third, its distances form an AP with a starting term of 5 and a common difference of 10. The total distance fallen at any second is the sum of this AP. By analyzing this arithmetic progression, Galileo first proved that the distance fallen is proportional to the square of time. Tracing the compounding chart on your left, see how this AP sum directly models gravity, acoustics, and the steady progressive acceleration of vehicles, establishing the fundamental link between arithmetic sequences and physical motion. Today, we have explored the beautiful linear structures of arithmetic progressions. We learned how sequences grow steadily by a common difference d from a starting term a, and derived the predictive NTH term formula. We proved geometrically, by fitting two staircases together, that the sum of first n terms is n over 2 times 2a plus n minus 1 times d. We verified how Gauss solved the natural sum, and how AP models auditorium seats, compounding saving deposits, and gravity acceleration. As we observe the progressive summary web, trace how staircases, formulas, savings, and gravity fall in perfect mathematical harmony. These linear growth equations are the silent models running our technology, predicting market values, scaling acoustics, and structuring computer memory. By mastering AP, you hold the keys to advanced calculus and numerical analysis.